wants to still discuss. Okay, our next speaker today is Tobias Fritz with his talk, What is Probability Theory? Please go ahead.
Yeah, right. Thank you. So first of all, sorry about my technical problems, but now I hope everything is going to be working. So I've decided to give a bit more of an experimental talk in a sense, which will hopefully be of interest also to a broader audience. Since I feel like there's something to contribute, something that we can do as category theorists in the foundations of probability and kind of deriving things, what the theory looks like and to these philosophical aspects. So to clarify what actually the question is here, I guess most of you will know that there's this endless and long-standing debate about what probabilities are. So are they subjective, are they objective? There's Bayesian statistics, frequentist statistics, and so it's a kind of very long and kind of maybe still sort of unclear discussion about what probabilities are, but that's not really the question I want to address here. The question that I want to raise is more like, what is probability theory itself? And also in some sense, what should it be? And so that's the question that I want to focus on. I mean, the two questions are certainly related, but I think the second question is maybe more fruitful, especially in our context. And so, well, part of the reason for why I think this question is fruitful is because I want to argue that category theory can provide new kind of input into this kind of question. But so I want to clarify the question first a little bit more by making it more concrete. And so suppose that you've never heard of probability theory. You don't know what probability is. Maybe you're Laplace or someone like that. And you encounter situations which somehow contain some apparent uncertainty. And then you realize, well, there is some kind of demand for a mathematical theory of this uncertainty. So for example, if you want to predict the weather, or like in machine learning, predict the next token, this somehow seems to be uncertain in some sense. Or, well, even if fundamentally it is not. I mean, this might be something that is, if you just have, for example, for the weather, a complete model of all the physics, then we don't need any sort of mathematical theory of uncertainty or randomness here. Since then, well, we can just run the laws of physics, we can make the perfectly accurate prediction, and then we don't need any such thing. But in practice, that's not how it works, right? In practice, we do have some uncertainty, and we need some ways to reason about this. And so a priori, it's not clear if different types of uncertainty really require the same type of reasoning about them. I mean, it's conceivable that, for example, the reasoning that you use to think about uncertainty about weather prediction would be totally different from the type of mathematical formalism that you would use for developing your theory of noisy communication and error correcting codes and this kind of thing. Or even to take a more extreme case, probability theory also gets applied in situations where there's only one sample. Like when we talk about the entire universe, we make observations about the whole universe and then kind of reason about that and try to update our beliefs about that. Should that really follow the same mathematical model as the first kind of thing? I don't have an answer. It's more like a question that I want to raise. And I kind of want to argue that using categorical machinery, we can approach these type of questions in some sense. But yeah, first of all, does anyone have any thoughts on this and any potential answers? Yeah, what do you think? What should probability theory be in a sense as a mathematical theory?
Maybe it can help if you also briefly show the previous slide again.
Sure.
Yeah, in my opinion, and I come from the world of physics, is that probability theory is a theory of knowledge, and also, and in that sense, physics is a misnomer. Physics is the set of our probabilistic understanding of the world, and in that sense, there are no deterministic physical laws. What we call as deterministic is our understanding of how nature works. And of course, that inherently has uncertainty in it. So I think probability is the order of human existence. In other words, otherwise we would be God, we would know everything. So just because we're humans, we need a theory to deal with our uncertainty. So actually, I totally concur.
Yeah. So
there is no physics, and even I'm a physicist. I say
that sounds interesting. Can you maybe clarify a bit more what role the uncertainty plays in that, in particular in the knowledge aspect?
Yeah, I mean, you have a partial observations, and then you try to make predictions. Basically, you want a theory, you want a predictive theory, because to have a theory that is based just on the current observations is kind of like trivial. You already have the observations, you don't need a theory for that. So the important thing is to see what's coming up next. Or if you change the physical parameters, what's going to happen. So you want the ability to predict. And that's why I think you need the probability theory. So I think we should replace physics with probability theory. That's my
interesting. Yeah, thanks. So it's sort of a whole theory of scientific theorizing and prediction. Yeah.
And that's the essence of the whole story about quantum computing and quantum theory versus classical theory. Quantum mechanics is not a description of how the world behaves, but how we understand it to behave, or how we don't understand it to behave.
Yeah. Does anyone else have their own answer? In particular, maybe if it's a quite a different one. Okay, then I guess I'm gonna continue for now, and then later again ask for kind of opinions and this sort of thing. Okay, yeah. So as I already said, I think it's unclear if all these different situations should follow the same mathematical model of uncertainty. And I think what Yannis was saying, we will still want to have more than mathematical formalism for this uncertainty and the prediction making. And so kind of related to my previous bullet points here about the different types of things, different types of situations, we can also try to distinguish kind of different types of uncertainty maybe a little more. There's something like when you flip a coin, something that is more in the direction of relative frequencies. Then there's degrees of belief. For example, so degrees of belief are often also just purely phrased or expressed in numerical terms. So in the same way as relative frequencies, right? They're both numerical values. But does that really need to be the case? And if so, I mean, maybe yeah, sure. I'm not saying that shouldn't be the case, but how do we actually justify this? And I mean, I know some ways, and we could just to talk about this, but mainly I just want to raise the question here, and to indicate that these numerical values are at least not completely obvious. I mean, imagine again questions like about the universe, or how do you quantify your belief in the existence of God? This kind of thing. That's right. A sort of an economist would basically force you to quantify it, and maybe one can ask if this is really justified. Then yeah, things like nighty and uncertainty that involve things where we don't even know what kind of distribution we should assume as our prior, for example, as our belief before we make any observations. So I feel like a little bit the type of question like, does AI pose an existential risk? Might fall in this category where we just have a lot of ignorance about this kind of deep questions that are relevant and answering them. And so all of these considerations, so as a kind of interesting side note, I realized that probability theory is somehow quite special as a mathematical subject, in the sense that it's supposed to be something like a science of uncertainty. And in that sense, it has a much stronger moral component than other areas of math do. Like, I don't know, take, well, category theory itself, or just algebra doesn't have any sort of designated purpose, but probability theory does. And so in a sense, we're kind of more subject to kind of making sure it actually serves that purpose. Okay, so now let me get a little bit more concrete and talk about mathematical models, and also kind of want to indicate, and similar to the diversity of these different types of uncertainty, that there also have been many different types of uncertainties that have, sorry, different types of mathematical models that have been proposed for reasoning about uncertainty. First of all, of course, ordinary numerical probabilities, which are just numbers, real numbers in a unit interval. But then there's also the concept of possibility theory. This is basically probability over the tropical semi-ring, which means that we multiply probabilities by adding the numbers. So it's more something like a theory of risk, maybe quantifies risk, that when you have independence events and that the risks kind of add up, and instead of summing them for disjoint unions, we would just take the maximum. Things like, yeah, various types of, I mean, logics for reasoning about uncertainty. There's something called fuzzy measure theory, which is again distinct from fuzzy logic. There's various formalisms like the Stemster-Schaefer theory for when you have ranges of probability values. Well, when you really kind of find yourself unable to give a precise value for quantifying your belief, then maybe you can at least have a lower bound and an upper bound, and then that are numerical values, and this is what this theory implements. So then so then the question is on what grounds do we actually choose between these different mathematical models? Again, I don't really have an answer, and I'm also somehow relatively ignorant of the philosophical literature and all of this, but I mainly just want to kind of raise awareness of this kind of question. Yeah, does anyone have any thoughts on this, and on what grounds do we choose? What do you think?
Could you maybe give some more intuitions about the possibility theory? Like,
Yeah. I mean, I can tell you the definition of what is called a possibility measure. It's just like a probability measure, but where instead of having sums for disjoint unions of events, one takes the maximum, and instead of having products for independent events, then we have sums. And maybe one can think of it as a little bit like quantifying risk or something like that in a sort of worst case sense. So if you have a large number, that will be bad because it's risky. But if A or B may happen, then the worst case risk is kind of the maximum of the one of A and the one of B.
then I
Again,
guess,
yeah.
yeah, sorry. Yeah, thank you for the answer. Yeah,
Yeah,
then I
sure.
guess one way of maybe choosing between the first two is what one wants to measure. If I want to measure like the risk, or I want to measure the probability.
Exactly, but then we have some intuitive idea of maybe risk, and then we still need to translate that into some mathematical model. But I guess more like the kind of, yeah. Yeah, I guess that goes in the direction of an answer, but yeah, how do we, and that is actually also closely related to the kind of answer that I want to give, which is need to see for each particular situation, what is our intuition about the type of uncertainty that is in there and the properties that it has. And I kind of want to argue that one can think about these properties and try to formalize them in categorical terms.
One, I mean, I guess related to what Elena has said,
Mhm.
is that even for the same problem, two, let's say, agents might have different things they want to do. So, for example, if I'm going on a trip, I want to buy some insurance, say for health insurance. The insurers and me have two different interests. I'm a little bit more like doing possibility theory, at least worst case scenario. So I want to make sure that things could be bad, but they're never going to get too bad. On the other hand, the insurer, if one wants, because of the law of large numbers, is perfectly good with doing the numerical probabilities in 0, 1, because it's going to have a lot of people buying the same insurance. And what are the odds that 1,000,000 of them are going to get hurt, right? So for situations where there's repetition, where there's IIDs or things like that, then the numerical probabilities are a posteriori justified by pretty much the laws of probability theory, even definitive theorem. But for other agents, things could be a little bit different, even on the same problem.
Yeah, that's a very nice example. Thanks. Yeah. Mm-hmm.
And maybe I cannot provide a very insightful opinion on that, but I have a question about this. As you said, there are so many different frameworks, except the ordinary numerical probability theory. So I'm quite curious why this ordinary numerical probability theory is so popular or becomes the mainstream in this in our scientific world, right? Because in physics we use that, and also if you like the Fields medal, there are a lot of winners in this probability theory, and they use this ordinary numerical probability instead of others. So I just curious why this is so successful and instead of other frameworks.
Yeah, that's a great question, and I'm not sure if I have a complete answer, but at least a partial answer in that somehow for many types of uncertainty, it does seem to be the most relevant kind of mathematical framework, and there are some justifications for that, like things called these Dutch book arguments, for example, that one can use in particular in a maybe more economics context, and again to argue that degrees of belief of a person of an agent should be numerical probabilities, because you can always ask, well, how much would you be willing to bet on your belief that X is true? and that way, and then you can compare this bet with how much they're willing to believe, how much they're willing to bet on other things, and that kind of gives you a ratio, and then you can basically define numerical probabilities in those terms. And in a more physics context, maybe it has to do more with relative frequencies again. That the things that we then observe are just kind of relative frequencies, and then it's natural to also formalize our degrees of belief, in particular degrees of belief about relative frequencies and repeated trials, to formalize those in the same way. But maybe it's, and as Paulo was saying, there's some also formal justifications for this, but maybe it's not the only way to do it. Yeah.
Okay, yeah, but I have another question, like the philosophical question, like I'd like to see this numerical probabilities as interpolation of the belief. So if the probability is 0, then we tend to say that, well, this will not happen, and if it's 1, we say it must happen. But as we know that the one with probability 1 will not always happen, right? It's not deterministically true. So I got confused by this philosophical problems.
Yeah. Actually, this is what I personally think would be one of the maybe most interesting also mathematical alternative models, where one has an additional distinction between events of probability 0 and events that are actually impossible. That one just would maybe allow an additional distinction there. And yeah, I haven't really, let's say, developed this mathematically yet.
Okay,
but yeah, I think this in particular could be an interesting direction. Okay, so yeah, thanks for all the input and comments. But yeah, so I think I'll continue now so that we can also get to the category theory. But before that, I briefly want to say that even for these ordinary numerical probabilities, if you develop this more in an, measure theoretic way, there is, again, we're kind of faced with the same problem again at another level, as in what is actually the most adequate mathematical formalization. And so the one that's used is this Kolmogorov's definition of probability measure with this countable additivity condition. And then again, as Lehau was saying, with the Fields medals and all that, this is the one that probability theorists have basically universally adopted. I guess it just also works very nicely as a mathematical theory. On the other hand, Bruno De Finetti was, kind of also a well-respected probability theorist, was going to say, no, you're doing it all wrong. And the P should only be finitely additive. And he somehow, I don't actually know all that much about this, but also had philosophical reasons to having to do with, again, what probabilities are to pursue this type of approach. Okay, just the same kind of problem again at another level. All right, and so now let me get to the kind of a way to think about these problems in categorical terms. And this is maybe also going in the direction of what Yannis was saying. And I guess many of you know that we have this framework of symmetric monodal categories that provides a way to at least in many situations, have some kind of meta theory of scientific theories, where you can say that, well, a symmetric monodal category is a certain kind of environment for some kind of theory in which one can develop models of the world, like quantum theory with quantum processes, probability theory with Markov kernels. These are symmetric monodal categories. So the idea being that we have processes, each process can have an input and an output, and these are kind of supposed to be the building blocks in our mathematical model of the world. And this can model either an actual system in the world, or it can model something about an agent's belief, where the input might be something that the agent observes, and the output would be how their belief changes or how they act, these kinds of things. Okay, and so now it's natural to assume these form a symmetric monodic category. But yeah, ultimately the goal of probability theory then would be to have the theory of uncertainty. And so that means that we need to have, well, we should have some notion of what uncertainty means when we have such processes. And what it means, and we saw things like this now in Eleanor's talk as well. I think a process contains uncertainty if when you execute it twice with the same input, it's not guaranteed to give you the same output. That is ultimately, to my mind, what uncertainty means or is about. And so here that means in order to express this condition or this property in the categorical framework, we should have this these copying morphisms and noting by bullets. So my string diagrams go from bottom to up. So same as in Eleanor's talk. This is sort of a precondition that needs to be satisfied in our process theory in order to talk about uncertainty. And yeah, I want to kind of emphasize that these are a property of our model. These are not necessarily actually physically existing processes, but just part of our modeling framework. Okay, and so then Paolo already mentioned this kind of consistency, numerical probabilities justified in terms of De Finetti's theorem and some kind of consistency statement there. And I think we have something, when we have such a general framework, how do we actually arrive at numerical relative frequencies? So I think relative frequencies should always still be numerical. If you flip a coin 10 times and you get 7 heads and 3 tails, that's clearly a numerical thing, no matter what. And I think, well, one can still consider this in a general such process theory by just saying, well, what happens when we use the same input for, let's say, 10 copies of the process, and then we just get something like some uncertain outputs, for example, degrees of belief over the various possible outputs, and then we can still kind of condense that into something numerical and, for example, ask, well, what is our strongest belief about the number of heads and the coin flips? So that's how numerical probabilities, in a sense, automatically come up. Another piece of structure then would be the deletion morphisms. We can just ignore the output of a process. Again, I don't want to assume this as a physical kind of mechanism, but just in our mathematical modeling framework, suppose that we just have something that lets us ignore outputs. So then we arrive at the definition of Markov category. And yeah, this is kind of similar, essentially the same as in Eleanor's talk again, symmetric monodic category with this extra structure. And here I'm assuming the normalization, since, well, it's kind of intuitive now, natural, this should hold, that when you just ignore the output of a process, then you might as well just not have considered it, executed it, or considered it in your model to begin with. Okay, so basically the main point of my talk is to express the idea that Markov category in general can be conceived of as a mathematical theory of uncertainty, and conversely, that this is now a general categorical framework for mathematical theories of uncertainty. And now we can use this framework and try to think about my original philosophical questions on what grounds do we choose and which one is appropriate in which situation. And to go about that, we can, well, we probably want to impose additional axioms. Or we may even want to choose a particular Markov category. But if, let's say, we're sort of open-minded about what our exact mathematical model of uncertainty is, well, then we can just try to formalize our intuitions about how uncertainty behaves and impose these as additional axioms. And then try to kind of classify the possible Markov categories that satisfy this. And then maybe one doesn't even need to choose any particular Markov category. Maybe one can even just work with a free Markov category subject to suitable axioms. Okay, and so now towards the end, I want to say a little bit about the axioms that we consider and that we work with on a kind of daily basis in Markov categories, and also how they're related. And to kind of give some examples about such axioms and how they formalize our intuition about uncertainty. So the first one, already we saw this in the previous talk as well, is the existence of conditionals. So maybe I don't have to go all that much into this, that every process that has two outputs, we can sort of factor it into a process as on the right-hand side, where we only have one output, the output X is generated first, and then a second process where the output Y is generated. In order to generate that, we should allow some dependence on both the original input and the first output that was already generated. So this is very intuitive somehow, that uncertainty, even if the processes contain some intrinsic uncertainty, that they would satisfy this kind of condition. So I think it's a natural axiom to impose. Another type of axiom that encodes some intuition about uncertainty is what we've called a positivity axiom. Whenever we have two processes that can be composed, so two composite morphism GF, and if this one is deterministic, by which I mean that it contains no uncertainties, so that this equation actually holds for GF. In this case, we automatically get this equation as well. And the intuition behind this is that if we have a composite deterministic process, where the first step, so the F, may do something with uncertainty, then it doesn't matter if we do this first and then use the output of that as input to the other process, or if we do basically the two things independently. We do the entire computation on the right-hand side, we just do the entire computation, and independently, we just do F. So this, again, formalizes the kind of intuition. And yeah, just happens to be true in measure theoretic probability as well. And finally, there's some causality axiom, as we call it, which encodes some kind of form of causality. And so imagine that you have an equation between processes as on the left-hand side. And this is kind of saying that in the future of F and G, one either performs H1 or one performs H2. And if the overall kind of uncertain things that happen do not depend on which choice we make, then it also doesn't, this property is still true if we also observe the output of F. So that's what's happening on the right-hand side here, sort of observing the output of F as well, because we consider that also, we copy that and consider it as an additional overall output. While on the left-hand side, we do not observe the output of F, since it's just an eternal wire. Yeah, so kind of whether we do H1 or H2 in the future of G does not influence the past of G. This is how one can think about it, and how it implements a form of causality. Again, this is true in measure theory probability. If we use ordinary numerical probabilities, it's false in other Markov categories. In particular, it's false if you allow negative probabilities. Okay, so yeah, just to say a little bit more about these types of axioms. These are, in some sense, also one can consider them as kind of information flow axioms, since they're somehow about how through information flows through these diagrams, what properties this information flow has. And these are kind of the main axioms that we have so far. And it's kind of curious that they seem to fall in a total order. So conditionals imply the causality axiom. That's not so difficult to see. What's been more surprising and a more recent result is that the causality axiom actually implies the positivity axiom. And then we have a few variations on these that are kind of intermediate, but still, and it's a total order. Not sure why that is. Yeah, if there's any sort of deeper reason for that, and or maybe it turns out to fail if we consider other ones that are not yet discovered. So I'm pretty sure there are more also of these axioms to be discovered, and maybe trying to think about the sort of philosophical questions I had phrased at the beginning can be a helpful way to go about it. Also just looking, maybe trying to develop, these other mathematical models for uncertainty. What are these kind of information flow properties of these Markov categories? And what intuition do these encode about uncertainty? That's also, I think, quite an interesting question that hasn't really been considered yet. And finally, as far as just ordinary probability theory is concerned, what's also completely open, and I have no idea how to even approach this problem, would be to find something like a complete characterization of all information, these information flow axioms that would hold in ordinary probability if we just take finite sets and then stochastic matrices or Markov kernels between them. Yeah, let's say we just restrict to a particular type of logical condition, let's say an implication from one equation to another equation. So the positivity axiom and causality axiom have this form. Then can we characterize all these types of conditions, all these properties that are true in this particular category? And again, I have no idea, and I don't even know how to approach this problem. Okay, so with that, I'm at the end, and if we can have a bit more discussion, yeah, I think that would be nice. Also, oh, actually, I see also time is pretty much up. So anyway, yeah, thanks for listening.
Okay, very good. We still have a couple of minutes, so are there questions or comments that we can make now? And there will be also more time at the end of the next talk after that question time. But please feel free to intervene.
Yeah, maybe I have several questions. And first, thank you for the nice talk. And actually, I'm a huge fan of this Markov category theory, and so I really appreciate this work. And I'm personally extremely interested in causal reasoning in this maybe in this setting. And sometimes I want to advertise this framework to other causality researchers, and sometimes I receive some doubts like, well, we already have the results in the the category of standard measure spaces, and also some people said that, well, the category theory is very sensitive to the axioms you make. So if you change a piece of a small axiom, then the theory is changed very very huge sense. So how do you like this kind of thoughts?
Yeah, thanks. That's interesting, and I think I have a good answer to that, namely in that we do have, the standard theory of Bayesian networks and basically Pearl's causality things, the D-separation criterion. We've developed all of this for Markov no, sorry, I shouldn't say all of this. I mean, that's just developed at least the D-separation criterion. There's already also some work on interventions by Fabio Zinassi and Bart Jacobs, Alex Kissinger. So these things have been developed, and I would say a good argument for that type of community would be to say that, in particular, the D-separation criterion that we have, I would claim is actually simpler than in the usual formulation of directed acyclic graphs, where if you look at it for the first time, or it just looks very convoluted and kind of incomprehensible. And the formulation in terms of string diagrams is actually just about topological connectedness. So that this will be one advantage, or one way, for one reason maybe for that community to be interested in it.
Yeah, personally I agree, but it's still very hard to convince other people to And another question is like, you claimed in your previous talk, like, the macro category is basically the most general setting in which you can do causal reasoning. And also you said that the landscape of macro category is really huge. So I'm wondering if you have really looked at, maybe macro categories from other fields instead of probabilities, for example, from geometry or abstract algebras, and there are some macro categories, and you can generalize your results in the causal reasoning to this new directions, and try to find some novel and interesting results?
Actually, unfortunately, so far no, because there's only so much time, and I feel like it's also too much to do for the and so what we're doing, I would say, is actually the main focus. Maybe kind of in contrast to what I've now been talking about, our main focus is more like on ordinary probability theory, measure theoretic probability, and to try and redevelop that in categorical terms as much as possible. So we've looked into other Markov categories so far, very little, but kind of my point is to say that there's a lot of scope here of things to be done. But yeah, we haven't done it.
Yeah, okay, I see. Yeah, thank you.
Thank you. Okay, I think we are out of time, so let's thank our speaker.